This is about interaction of electromagnetic radiation with the matter. Now we'll understand very important concept, condition for laser action. So we have some conditions. Suppose if the atom stays in the previous slide you have seen, if the atom stays up to 10 power minus 8 second, it is impossible to produce the laser. I can't have this stimulated emission within 10 power minus 8 second. So I want this atom to stay in the excited state for little more time. Instead of 10 power minus 8, 10 power minus 3. See, 10 power minus 3 is greater than 10 power minus 8. It is not plus, it is minus. 10 power minus 8 is nothing but 0.700001. Whereas 10 power minus 3 is nothing but 0.001. That is the thing. So I want this atom to stay in the excited state for little more time. Then only I can have the laser beam. That is first condition. First condition is I want atom to stay in the excited state for little more time, 10 power minus 3 to some 10 power minus 4. That is one condition. So the one more condition is N1 must be greater than N2. Can anybody tell me what is N1 is greater than N2? What does it mean? Can anybody?
Ground state and exit.
Number of atoms.
Very good. Number of atoms in the ground state and number of atoms in the excited state. I repeat again. I want atom to stay in the excited state for 10 power minus 3 to 10 power minus 4 second. Naturally, what happens? N1 is greater than N2. It is naturally. Atoms in the ground state is greater than atom in the excited state. If this is the case, I can't have a laser beam. So I want atom in the excited state should be greater than atom in the ground state. That means, suppose if it is ground excited state, it is ground state. If there is one atom in the ground state, I want more atom in the excited state. There are 4 atoms in the excited state. There are 2 atoms in the ground state. Now I can say N2 is greater than N1. So first condition is this. I want atom to stay in the excited state for longer time. Second condition, I want more atom in the excited state than the ground state. These are the 2 conditions for laser. We'll look into it. So in detail. This is the ground state. This is the excited state. Energy of the ground state is E1. Energy of the excited state is E2. Okay. And this is atom in the ground state. Whereas I'll take one more condition. Whenever you pass some photon to this, it absorbs and it gets elevated to the excited state. It stays up to 10 power minus 8 second only. After that, it will come back to ground state. So I want this atom to stay for little more time. For that, what you have to do? So we'll see that. This is the ground state excited state, E1, E3. Now what I am doing here, this is the ground state. This is the excited state. So what I'll do, I want, suppose if the atom gets elevated from here to here, it stays for 10 power minus 8 second. So suppose if it stays for very, very less time, that is 10 power minus 8 second, I can't produce a laser. So what I'll do, purposefully, I'll introduce one more state between these 2 states. Understand? Once again. So this is the ground state. This is the excited state initially. So since I want atom to be in the excited state for little more time, so purposefully in between these 2 energy level, I'll introduce one more energy state. So how do you introduce? Is it possible? Let me take one example. In semiconductor, we have 2 types of semiconductor, right? One is intrinsic and extrinsic semiconductors. In intrinsic semiconductor, what happens? This is the pure semiconductor, intrinsic, right? So, but what happens? What is the let me ask you a question. I'll ask you the question first. So we have already semiconductor, that is intrinsic semiconductor, silicon and germanium, naturally, right? Still, why do we need extrinsic? Can anybody? Prithviraj, can you answer? Prithviraj? Let me ask you the question again. We have 2 types of semiconductor, intrinsic and extrinsic. Already we have intrinsic semiconductor, right? Silicon and germanium. Still, why do we need extrinsic? Why I have to add impurity to the intrinsic semiconductor? Then I can obtain extrinsic like N-type and B type. Why? What is the purpose of that? Purvaj? If you don't answer, we can't complete the syllabus. Urvaj,
Sir, I don't know, sir.
Rajat, Rajat, Rajat. If you don't say anything, I may have to mark you absent.
Yes, sir.
Amrutamani for conduction purpose. Okay, partly right. Sangeeta, can you? We have intrinsic
Hmm?
already. Why do we need extrinsic?
For conduction.
For conduction. So even the intrinsic also conducts, right? Suppose if you increase the temperature, intrinsic also conducts.
Sir, for more conduction,
Very good. Who is that?
Dhanraj BMC.
Okay, to increase the efficiency. Very good. Arshit and both of you answered very well. So in the intrinsic, what happens? The conductivity will be limited. So conductivity will be limited by adding impurity to that intrinsic semiconductor, that is silicon and germanium. I can increase the conductivity. So that is the purpose of extrinsic semiconductor. By adding impurity, aluminum or phosphorus, whatever, you add impurity to the intrinsic semiconductor so that in turn you can increase the conductivity. That is the purpose of extrinsic semiconductor. There, what you do, you do the doping. Doping is nothing but adding impurity. Similarly, here also, I want atom to stay in the excited state for little more time. So I will include one more type of semiconductor, one more type of any atom. So say for example, if it is carbon dioxide laser, a carbon dioxide laser has got two energy level, that is ground state and excited. Suppose if I consider. Now I'll introduce one more impurity. Say for example, nitrogen. Nitrogen has got two more energy level. So one of the energy level of nitrogen acts as a metastable state. Here it is called, this is one kind of atom, this is another kind of atom. This is called metastable state. This is called metastable state. Hope all of you understood what is the purpose of introducing one more energy level. I repeat again, I have two energy level, grounded state and excited state. Suppose if I pass some photon, this atom absorbs this and gets elevated to the excited state. Here it stays only up to 10 power minus 8 second. Suppose after 10 power minus 8 second, it will come back to ground state. If that is the case, I can't produce a laser. So I want this atom to stay in the little excited state for little more time. So purposefully, I'll introduce one more energy state between these two energy state. This one more energy state is called metastable state. I'll ask you a question in the next class. Please understand. This is called metastable state. Now what happens? Atom will not come to the ground state directly. It follows some protocol. So whenever atom has to come to the ground state, it should follow the energy level. Now this is my ground state. This is excited state. Then this is the third energy level. This is first ground state. This is first excited. This is second excited. Or one energy level, second energy level, third energy level. So atom will not come from 3 to 1 directly. No, it follow protocol. That is, it has gone from 1 to 3. Now it will go to the metastable state here. Okay, it will go to the metastable state. Then from metastable state, it will come to the ground state. Now here it stays for 10 power minus 8 second. Now it stays for 10 power minus 3 to 10 power minus 4 second. This is called metastable state. One of the condition for laser is metastable state. Let me show you. Okay. This is ground state, excited state. This is E1, E3. Why it is E3? Because there is one more state between. It will go to ground from ground state to the excited state. Then I have one more energy level between E1 and E2, that is E1 and E3, that is called metastable state. Now atom has gone from E1 to E3, then it will come to E2, then it will come to E1. Now here it stays for 10 power minus 8, whereas here it stays for 10 power minus 3 seconds. That means what? In order to produce laser, only two energy level are not sufficient. Remember, this is the first condition. In order to produce a laser, there should be three energy levels. That is, one of the energy level is called meta stable state. This is called meta stable state. Hope it is clear. Now, nobody asked me, sir, why it stay here? Let me write here. Why it stays for 10 power minus 3 second, whereas here 10 power minus 8 second? The reason is very simple. As the energy level goes on increases, the time of staying in that energy level goes on decreases. Okay, remember this. So it stays for here like 1, 2, 3, like that. Here it stays for 1 second, like this. As it energy level goes on increases, the time of staying in that respective energy level decreases. Remember that. Here, so it is 10 power minus 3 seconds here 10 power minus 8 seconds. Suppose if there is one more energy level here, 10 power minus 10 second. Here one more energy level, 10 power minus 15 second. That means as the energy level goes on increases like 1, 2, 3, 4, like that, the time of staying there in different energy levels in the higher energy levels goes on decreases. That is the reason why atom in the metastable state stays for little longer time, that is 10 power minus 3 to 10 power minus 4. This is one of the condition called metastable state. Okay. In equilibrium, E1 is more populated than E2, so we can't get stimulated emission. So we need to inverse this condition. Next, we have another condition. This is E1, this is E3. Atom in the ground state. It goes to the excited state, then it will come to the metastable state. It stays up to 10 power minus 3 seconds, then it will go to the ground state. Here, look at here, since it stays for little more time, can anybody tell me atoms in the ground state is more or atoms in the metastable state is more? Yeah, you're saying. Sangeeta, you are saying something?
In the metastable state.
Very good. Look at here. There are two atoms in the ground state. There are four atoms in the excited state. That is metastable state. The energy level next to the ground state is called excited state. This is ground state. This is also called excited state or metastable state. So as I told you initially, what is the first condition to produce a laser? I want atom to stay in the metastable state for 10 power minus 3 to 10 power minus 4 second. This I have achieved by purposefully introducing one more energy state between two energy level. This is done in the previous slide. Second condition, what is the second condition? I want more atom in the excited state than in the ground state. Since atom stays in the excited state, that is metastable state, for little more time, more atoms stays here. Since atom which stays in this state will be, the time of that will be more. So more atom will be accumulated in the energy level, in the state N2. This is N1, this is N2, this is N3, right? So N2 is greater than N1. So we have achieved both the conditions. This process, what is population inversion? Population inversion is nothing but keeping more, keeping more atoms in the excited state than the ground state is called population inversion. I repeat again, what are the conditions of laser action? First condition, metastable state. Second condition, population inversion. What is metastable state? In order to keep the atom in the excited state for little more time, that is 10 power minus 3 to 10 power minus 4, purposefully introducing high energy level between two energy level is called metastable state. What is population inversion? Keeping more atoms in the excited state than the ground state is called population inversion. So I'll be asking you the question next slide. See, this is the condition for population inversion. That is N2 is greater than N1. Keeping this is N2, this is N1. Hope it is clear. Next, what are the requisites of laser? One is excitation source, active medium, then laser cavity. Let us understand what is this excitation source. See, we have studied in initial, right? Three process. One is induced absorption, spontaneous emission, stimulated emission. So what is a stimulated emission? Principle of laser is stimulated emission, right? This is the excited state. This is the ground state. So atom is here means already it has undergone induced absorption, right? So atom will not go to excited state directly. No, it has got no energy. It will not go to excited state by itself. So before sending the atom, you have to pass some energy. Atom will be in the ground state. You should give some energy, h mu. Then only it gets elevated to the excited state. So in order to send the atom from the ground state to the excited state, you have to pass some energy, right? That energy is of either light energy, or you can give, suppose if it is semiconductor, you can give some high forward bias voltage. So those things are possible. That is called excitation source. I repeat again, the principle of laser is stimulated emission. In stimulated emission, in order to occur stimulated emission, I want atom to be in the excited state. So how do you send the atom to the excited state? By passing some energy. There should be induced absorption, then only you can have stimulated emission. Without induced absorption, you can't have a stimulated emission. This is second case, right? First case will be atom in the ground state, you pass some energy, then only it goes to the excited state. This is first case, then only second case can occur. The first case is excitation source. What is the, I repeat again, what is the energy you need to send the atom from the ground state to the excited state? That is called excitation source. Either light energy you can use, or if it is semiconductor laser, you can use some high forward bias voltage. Okay. Then active medium. What is this active medium? So in order to, what are the condition of laser? First condition is metastable state, right? First condition is metastable state. And the next condition is population inversion. If these two are there, then only we can produce the laser. That metastable state as well as population inversion occurs inside the active medium. Hope it is clear. In order to send the atom from the ground state to the excited state, you need some energy, that is called excitation source. Active medium is nothing but we have two conditions for laser. One is metastable state, other one is population inversion, where that occur inside the active medium. And laser cavity is nothing but I have got some frame in inside of that cavity, that is called laser cavity. I'll show you here. Okay. Excitation source, I just know I told you. The excitation source provides energy in an appropriate form for pumping. Pumping is nothing but sending atom from ground state to the excited state. This is ground state, this is excited state, atom will be here. You pass some energy, h mu. By passing some energy, it absorbs, then only it gets elevated. That is called excitation source. What are the things you can use? Either you can use light energy, either you can use electrical energy, electrical pumping. This excitation source is also called pumping. Atom from ground state to the excited state. Active medium. Active medium is one which population inversion takes place. Just now I told you, population inversion is nothing but keeping the atom in the excited state, more atom in the excited state than the ground state. That is called population inversion. Population inversion will exist inside the active medium. Laser cavity. Two mirrors. There will be two mirrors. I told you just there will be a frame. There will be two mirrors along with the active medium. Form a laser cavity. Inside the cavity, two types of wave exist. One type of comprises wave moving to the right. One wave may go like this. Another wave may go like this to the right side. Another wave to the left side. I'll show you the cavity now. You will understand. When two waves interface constructively, whenever two waves interfere constructively, which gives no phase difference, that can be considered as laser beam. If it's destructive interference, there will be a phase difference of phi. See here, this is the active medium. This is the excitation source where you need some energy to send the atom from a ground state to the excited state. Active medium is nothing but inside of that there will be a population inversion. There will be two mirrors. One is fully silvered. This is fully silvered because I don't want laser to escape. This is partially silvered. That means whenever two wave undergoes constructive interference, that wave comes out. Partially silvered is nothing but there will be some gap. That wave comes out of this cavity as a laser. Very simple. So this is the excitation source. Excitation source is nothing but there will be two energy level. This is You pass some electrical energy or light energy to send the atom from ground state to the excited state. Then atom was in the ground state, it gets elevated, it goes to the excited state. So this is called the excitation source, or it is also called pumping, either light pumping or electrical pumping. So depends on your requirement, depends on type of laser you can use. Okay, this is excitation source. This is the active medium. This is your active medium. What is active medium? There will be population inversion. That means more number of atoms stay in the excited state than the ground state. See, same thing. What all are the things happens inside the cavity? I have represented using some animations. This is the ground state. This is the excited state. Atom was here. Due to this pumping, atom gets elevated to the excited. It was here initially. See, initially it was here. After pumping, it has gone to the excited state. So there should be one more energy state. Then only we can produce a laser beam. That is called metastable state. So atom was here. It goes from ground state to the excited state. From this excited state, that is E3, it will not go to E1. It will go to E2. This N1 is the number of atoms in the ground state. N2 is the number of atoms in the metastable state. Now from E3 to E2, atoms comes from E3 to E2. It stays, more number of atoms stays in the N2 than N1. See here, there are 3 atoms here, there is 1 atom. So then from E2 to, or from N2 to N1 atom comes. So there will be 2 mirrors. This is called population inversion. Complete process is called population inversion. Let me repeat once again. So this is the excitation source. You pass some light energy or electrical energy in order to pump the atom from ground state to excited state. This ground state, excited state, you are given some energy, so it absorbs, it gets elevated. You purposefully introduce one more energy state called metastable state. N1 is the number of atoms in the ground state, N2 is the number of atoms in the excited state. Then atom from E3 to E2 it comes, and more number of atoms stay in the excited state than the ground state. So did I achieve N2 is greater than N1? Sorry, N2 is greater than N1. I achieved population inversion. This condition is called population. This is the one of the major condition to produce the laser beam. Okay. Now atom comes to the ground state. This is called active medium. How do you write in the examination? Very simple. Suppose if in the examination, if they ask you a question like this, what are the condition of laser? Explain. First, requisites of laser. First thing is excitation. Draw this diagram. This is not required. Only this diagram is sufficient. Excitation source. It is the source or energy required to pump the atom from ground state to the excited state. Example, light energy or electrical energy. You got marks. Active medium. Active medium is one which population inversion as well as metastable state exist. That's it. And it contains 2 mirrors. This is fully silvered. This is partially silvered. This is fully silvered. Okay. So now what you do? Atom is in the excited state. Now what you do? You pass some energy now. Because what is the principle of laser? Principle of laser is stimulated emission. Atom. Now forget this. You have to forget. Only these two you have to consider. This is excited state. This is ground state. Now you pass some energy to the atom in the excited state. This energy gets stimulated with this. Due to this process, atoms comes to the ground state. When it comes to the ground state, it emits 2 photons. One h mu and another h mu dash, let me consider. It emits 2 photons. This photon, which is this photon comes from this. Initially, you have given some energy, right? That photon is this. This photon is from the stimulated emission. These 2 photons will be coherent. Those 2 photons will be monochromatic. So it satisfies laser properties. It is highly directional. So these 2 beams can be considered as a laser beam. Again, so these beams travel throughout the cavity. So these two photons travel throughout the galaxy. Imagine the laser is produced, one wave goes like this, another wave may go like this, another wave may go like this, another way may go like this. Suppose if two waves, what happens if two waves interfere constructively, only that wave comes out of this partially silvered mirror. Only that wave comes out of this partially silvered mirror. Okay, when those two waves which undergoes constructive interference, only that wave comes out of this as a laser beam. If these two waves interfere destructively, they cancel each other, so that will not give you laser beam. See here, only two waves which undergoes constructive interference, that wave comes out of the partially silvered mirror as a laser beam. Okay, this is how laser works. This is the requisites of a laser beam. See here, when these two waves undergo constructive interference, that wave coming out as a laser beam. If it is destructive interference, there is a phase difference of pi. So this is one wave, this is opposite wave. So this will not give you laser beam, only constructive interference will give us laser beam. Hope it is clear. This is the condition for constructive and destructive interference, n lambda by 2. This is 2n plus 1 lambda by 2. This you have studied in your PUC. Okay. Next we have Einstein A and B coefficients. It is 15 minutes. Let me take. I'll just finish it. What is this Einstein A and B coefficients? In the previous class, we have studied three different processes. One is induced absorption, spontaneous emission, and stimulated emission. Now, using those three equations, actually, we derive Einstein A and B coefficient, energy density expression using Einstein A and B coefficients. Do you remember this equation? This is rate of induced absorption. In the last class itself, I have shown you this. You want me to repeat? Induced absorption? Can anybody? Ritesh? Are you there? Malcolm Batrango. Prithviraj?
Sir,
You want me to repeat the induced absorption, spontaneous and stimulated, then continue, or shall I directly take the equations?
sir, ಒಂದ್ಸಲ ಮಾಡಿ sir.
Okay. Okay, from here we have started. I'll not repeat again. I'll just quickly run through. In the last class we have studied this, right? There are three different processes: induced absorption, spontaneous, stimulated. In induced absorption, we got this equation because induced absorption depends on two parameters. One is number of atoms in the ground state as well as incident energy. This equation I've taken. Okay. Second is spontaneous emission. It is not dependent because in spontaneous emission you are not passing any energy. The atom by itself it will come to the ground state. So it depends on only one parameter, that is number of atoms in the excited state. So this equation I'll take. Third one, stimulated emission. In order to have the stimulated emission, you have to pass some energy, and also it depends on number of atoms in the excited state. I'll take this equation. I've taken these three equations. According to conservation of energy, induced absorption should be equal to emission. That is, we have two emission: stimulated emission and spontaneous emission. Stimulated and spontaneous emission. I'll use this equation, then I'll substitute. Okay. This is that equation. Just now I showed you this. Rate of induced absorption, it depends on two parameters: incident energy as well as number of atoms in the ground state. Rate of spontaneous emission, it does not depend on any external energy. So A21, N2. Rate of stimulated emission, B21, N2, EMU, because it depends on number of atoms in the excited state as well as energy you pass in order to stimulate. So I know this equation 1 should be equal to equation 2 plus 3, because according to conservation of energy, absorption should be equal to emission. There is one absorption, there are two emission. So rate of induced absorption equal to rate of spontaneous emission plus rate of stimulated emission. Look at this equation. What is our intention? Our intention is to determine what is the energy density. Energy density. That is my question. Where is energy density? Energy is here and energy is here. This is energy density. So just substitute. Take this and put it here. Take this and put it here. Take this and put it here. Just substitute. Induced absorption is this. I substitute here. It is not a regular class to write and show you. This is spontaneous emission, substitute here. This is stimulated emission, substitute here. I just substituted. Okay. What I need, look at this equation. E mu is here. My intention is to determine energy density, right? E mu is here and E mu is here. So what should I do? There is E mu left hand side as well as right hand side. What you do? You just take this to the left hand side. What happens here? I can't write B1 to this equation minus this equation. B21 N2 E mu will be equal to A21 N2. This is what you get. Here B12 N1 then E mu. This is what I get if I take to the left hand side. So this E mu here, this E mu here, take as a common. If I take out a common, B12 N1 minus B21 N2, right, will be equal to A21 N2. Yes, 2. The same thing I written. Now I need E mu. If I need E mu, that will be equal to this equation divided by this equation. So the same thing I written. A21, this is A21 N2 divided by B12 N1 minus B21 N2. So I got this equation. Hope all of you got this, no doubt. Take to the left hand side and just simplify and determine what is E mu. This is what I get. Next, E mu equal to, now what you do, just do some simplification. So here N2 is here. Take out B21 N2 as a common. So this N2, this N2 cancels. Remaining is A21 by B21, 1 divided by B12 N1 divided by B21 N2 minus 1. This is what you get. So how do you get this? Just take B12 N2 common outside of this equation. But, so I'll repeat again. This B21 N2 you have to take a common as outside. But this term is not there in this equation. So what you have to do? You have to divide. If that term is not there, B12 N2 you have to divide. But this common term is exist here. So minus 1. So this N2 cancels. Remaining is A21 by B2. A21 by B21, 1 divided by, there's nothing here because I cancelled. I've taken A21 this side. So 1 divided by B12, this B12 divided by B21 by N1 by N2 minus 1 because I've taken a common. So there is a minus 1 here. This is what I get. Now from Boltzmann law, so we have Boltzmann equation. What is this Boltzmann equation? Suppose if there are two energy levels, this is directly you have to remember. This is ground energy state and this is excited state. So what is the probability of occupation of atoms in two energy level? For that we have a direct equation, N1 by N2 will be equal to e power h mu by kt. This is the Boltzmann equation, you have to remember directly. The probability of occupation of electrons or atoms in different energy levels, thus ratio can be expressed as N1 by N2 equal to e power h mu by kt. This is Boltzmann equation. Now this N1 by N2, go back to this equation. This N1 by N2, right? For this place, you have to substitute the Boltzmann equation. I have substituted. Instead of this N1 by N2, I have substituted e power h mu by kt. I didn't do anything, just I have substituted. Okay. Next we have, this is also energy density equation, Planck's law. Planck's law is also speaks about energy density itself. Using Planck's law, we have the final expression of energy density as 8 pi h mu cube by c cube into 1 by e power h mu by kt minus 1. This is a standard. In this expression, you have to remember two equations. This is one equation. This is another equation. This is using Planck's law. Energy density equation using Planck's law. This is the standard equation actually. This is the standard equation. Now, Using Einstein energy density, we have obtained this energy density, E mu itself, left hand side. Using Planck's law, we have this standard equation. Left hand side both are equal, no. So can I equate right hand side? So I can equate this equation with this equation since left hand side is same. So by equating these two equations, look at here, 1 by e power h mu by kt minus 1, 1 by e power h mu by kt minus 1. But in place of a21 by b21, what we have? We have 8 by h mu cube by c cube, right? But e power h mu by kt minus 1, e power my h mu by kt minus 1, same. But in place of b12 by b21, there is nothing. So can I write b12 by b21 will be equal to 1? There is 1 here, right? If there is nothing, there is 1. That is the meaning of this. Okay. I'll just, compare this equation. By comparing these two equations, what I get? I get a21 by b21 equal to, this equation will be equal to this much. b12 by b21 equal to 1. Okay, that's what I have written. Okay. So look at this equation. So b12 by b21 equal to 1 means, can I write b12 will be equal to b21? That means what? b12 is nothing but sending atom from ground state to the excited state. This is excited state to the ground. This is induced absorption. This is spontaneous emission. Don't forget, by cross multiplying, can I write b12 equal to b21? That means what? This is rate of induced absorption equal to rate of spontaneous emission. That means what? What is a physical interpretation of this? Whenever atom get absorbs, spontaneously it will come to ground state. That is the meaning of this. Staying in the excited state is very, 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 very less, because the mathematical equation says that induced absorption equal to spontaneous emission. The moment it absorbs and goes to the excited state, within a fraction of a second, it will come to the ground state. That means what? If there is no metastable state, we can't produce a laser beam. That is the meaning of this. What is the physical interpretation of this? If there is no metastable state, or if there are only two energy level, we can't produce a laser beam. The moment it absorbs, within a fraction of time, it will come back. Because it is showing, this equation is giving that information. B12, that is induced absorption equal to spontaneous emission. That means what? If both are equal means the atom will never stay in the excited state. That is the meaning of this. The moment it absorbs, the moment it will come back. That is the meaning of this. So if there are only two energy level, we can't produce a laser beam. So what is the alternative? You should introduce a metastable state. Actually, metastable state I already explained to you. Actually, I'm supposed to explain after explaining this. So how we come to know we should introduce metastable state? That is just because of Einstein equation. That is just because of Einstein equation. Okay, that is the one of the physical interference of this equation. If there are only two energy level, we can't produce a laser beam. There should be one more metastable state in between two energy level. That is the physical interpretation of laser energy density equation. So look at this equation again. Sorry. So E mu equal to, because there is only one A. There is only one A, right? So can I write A instead of A to 1? Can I write just B to 1? So instead of B to 1, can I write just B? Because B12 equal to B to 1. So this shows that there is B12 equal to B to 1. There is one A, because there are no other A's. This B21 or B12 will be equal. This equation gives that information. So BB cancels, right? This cancels, because B12 equal to B12, this equation. So remaining is e power h mu by kt minus 1. That's itself. This is e mu. This is the final expression of the same thing I've written here. This is the final expression of energy density equation. Actually, I don't remember the year. Okay, just give me 1 second. 1905. 1905. This energy density equation was explained in the year of 1905. You just Google it. Actually, first laser, I'll tell you the exact time. Almost in the year of 1958. The first laser invented in the year of 1958. Practical laser. I repeat again. This energy density equation was explained in the year of 1905, whereas the first laser invented in the year of 1958. Almost some 40 to 50 years gap. Just remember, the physicists during that time took almost 50 years to convert from theoretical to practical. Just remember that this Einstein gave the theoretical information in the year of 1905 itself, but first laser invented in the year of 1958. See, to convert from theoretical